Lecture 14 is just a quick primer on synthesis. I wanted to go over some background and strategy for the process of converting a starting material into a more complicated product by use of several reactions in sequence. Usually in a textbook, you'll see problems that involve taking a given starting material and over several sequential steps, converting it into some target. The goal, of course, in the textbook is to make the student synthesize or put together their knowledge of chemical reactions and starting material and products formed and combine those in a clever and efficient way to create a target. In real life, though, usually the way it works is you are given some target and your job is to figure out where the most logical or cheapest or efficient starting material is that you could use any of your known reactions to convert that theoretical starting material into the target of your choice. For example, if we wanted to make penicillin, where would we want to start? Where could we start? And then from that starting material that we've chosen, what steps would we need to convert that starting material into your product? Now, theoretically, you could start from any starting material. Maybe that's a very cheap, very basic starting material. Maybe it's a more expensive one that would only take fewer steps to get to your target. So that is the goal of synthesis, is to start from a logical place and use the known reactions to convert it into product of our desire. Now, that means that you need to think in reverse. And that means that we need to know the reactions. We need to know what starting material can be converted into what products and what reagents we need to do that. We need to know their traits. Now, the idea of working backwards was formalized by a chemist called E.J. Corey. He was at Harvard at the time. I believe he's still at Harvard. He won the Nobel Prize for this in chemistry in 1990, quote, for the development of the theory and methodology of organic synthesis, specifically retrosynthetic analysis. So like I said, he was the first guy to really formalize this, to kind of take the logic of this and apply it in a systematic and, again, logical way. The idea of transforming a target into simpler precursor structures. And you repeat that over and over on the precursors to get further precursors until you get back to some starting material that is commercially available or otherwise easy to acquire. Let's try this using this target. Let's say we want to make this molecule and we want to figure out where we want to start from that will get us to this target in the most efficient and probably cheapest way possible. The way we write this is with a retrosynthetic arrow. This arrow here means that we are going backwards. And the idea is we're going to take this target and we're going to go backwards to some synthetic precursors that we're going to call synthons. These synthons are idealized versions of real molecules that we're going to call retrons. So this is some jargon, synthons and retrons. But just imagine that synthons are idealized disconnections from our target that give us simple precursors. And from these idealized synthons, we're going to come up with some real molecules that kind of mimic those idealized things. So, for example, here's the way that I would start doing a retrosynthesis on this target. I'm going to look at these specific bonds here, and I'm going to imagine disconnecting those bonds. So if I disconnect these bonds, this is what I would have. I could have a negative charge on a carbon here. That would be this carbon here, a negative charge there, and then a positive charge on this carbon there, right there. If I disconnected that bond that way, giving a negative charge on the carbon on the right, a positive charge on the carbon on the left, in theory, if I had these two pieces, they could come together and we could have that connection formed. I'll do the same thing on the other side. I'm going to imagine disconnecting this bond here, and if I disconnected that bond there, I'd give a negative charge on the carbon on the left, a positive charge on the carbon on the right, and I would have these idealized pieces. In theory, if I had these two pieces, we could combine them, the negative charge would come together with the positive charge, and we can make that connection. So these are my idealized precursors. Now, why did I choose triple bond here when I have a double bond in the product? Well, I chose a triple bond because I know, and we know now, that you can have negatively charged carbons on a triple bond, these sp hybridized carbons, because those are the acetylenate carbons, and those carbons can stabilize that negative charge. So if I had a triple bond here, it would be really easy to make these negative charges. Of course, we know that we can always easily convert the triple bond back into the double bond once we're done. That's easy. In fact, this is a cis double bond, and we know that we can easily convert a triple bond into a cis double bond using Lindlar's catalyst. So these are our idealized precursors. These are not real pieces, obviously. These are charged kind of intermediates. But let's try to think up some real molecules, some real precursors that mimic these idealized structures. Well, this idealized structure we can maybe get by having this molecule here, where the bromine gives us significant positive character on that carbon. Or maybe this aldehyde here, where the carbonyl gives us significant positive character on that carbon. Either of these pieces could, in theory, be attacked by a nucleophile at that site right there. And that would give us the connection that we're trying to make here. We've already mentioned that a triple bond where we want negative character on either side or on both sides could be formed in 2 steps by acetylene. All we have to do is remove the H from one side to get the negative charge on that side, and then remove the H from the other side to get the negative charge on that side. That's easy. That's a good retron from our synthon here. And this synthon here, we want a 3-carbon chain with a positive charge in the middle. We could get that by starting with 2-bromopropane. That bromine, again, would give us significant positive character on that second carbon. So now all we need to do is take these real precursors and use the reactions that we know to combine them and make the attachments that we need to get to our product. So let's try this. Let's start with this retron right here. We're going to start with acetylene. And let's imagine that we use NaNH2 to deprotonate our acetylenic hydrogen. That gives us the acetylide with the negative character on that triple bonded carbon. We can then, in a second step, add this retron here, and ideally our carbon would attack the carbon with the bromine, displace the bromine, and we'd get the connection that we want. We'd make that carbon-carbon bond, and we'd have our OH there. That's a problem, though. That won't work. The reason it won't work is that we have an alcohol that is acidic, and we have an acetylene, acetylide, that is basic. And remember that acid-base proton transfers always happen much more rapidly than nucleophilic substitutions. We always said that when we have nucleophilic substitutions, we cannot have acidic hydrogens around. Ideally, that acetylide would attack the carbon and displace the bromine. But because that hydrogen is acidic, that acetylide is much more likely to just grab the hydrogen, and that would extinguish our nucleophile. We would regenerate our acetylene from our alcohol here. Okay, so that doesn't work. This specific retron that we used, does not make sense in the context of how it would actually need to be used. So let's try another retron here. Let's try our aldehyde. So again, we'll start with our acetylene. We'll add an NH2 that would deprotonate our acetylenic hydrogen, generate the acetylide. Then we would introduce the aldehyde. Ideally, our acetylide would attack the carbonyl. It would displace the electrons onto the O, and that would give us an O minus there. And then simply in a third step, we could just add dilute acid or water, and that would protonate our O and make the alcohol. Now, remember when we added acetylides to aldehydes or ketones, we were doing two things at once. We were not only generating the carbon-carbon bond that we wanted here, we were also generating an alcohol on the carbon that was attacked, which is here. So we are killing two birds with one stone. We are using the aldehyde to act as an electrophile for our nucleophile to make our carbon-carbon bond and simultaneously give us the alcohol that we want in the desired position. Great. So now all we have to do is add our other side, add the isopropyl group. And like we said, we're going to add 2-bromopropane as our electrophile. So we've got our acetylide. We can take our NaNH2 and deprotonate our acetylide. And then in a second step, our acetylide would attack our carbon, displace the bromine. But again, we've got a problem because we have two acidic hydrogens on our substrate. The NaNH2 is not going to deprotonate the acetylide. Instead, it's going to deprotonate the alcohol, which is more acidic. So that won't work. If we try to introduce our substrate here to NaNH2, it's not going to deprotonate the hydrogen that we want it to. And there's nothing we can do to control that. So this doesn't work either. But the problem isn't the substrates, and the problem isn't the synthons or the retrons. The problem is the order. Notice that the problem here is the alcohol. We're making the alcohol first and then trying to deprotonate the acetylenic hydrogen. So what if we switch the order around? What if we first put on the isopropyl group? So we'll take our acetylene, deprotonate it with NaNH2, generate our acetylide. That acetylide would attack the carbon with the bromine, displace the bromine, and there we have made our carbon-carbon bond to our isopropyl group. That's this connection first. Now, when we add NaNH2, our only acidic hydrogen is the acetylenic hydrogen. So that would give us our acetylide. We could then introduce it to our aldehyde. That would make our carbon-carbon bond, kick the electrons up onto the O to give us our alkoxide, then protonate it in a third step to give the alcohol. That gives us this. So we're almost done. We've added the piece on the left. We've added the piece on the right. We did the proper order so that we would never have any acidic hydrogens interfering with our acetylene deprotonation. Now all we need to do in order to convert our alkyne into our alkene is simply to do a Lindlar reduction. Add H2 in Lindlar's catalyst and convert our alkyne into the cis alkene. So there we go. That's some logic, some use of retrosynthesis to figure out logical precursors, and then using the reactions as we know them to assemble them in a way that works. Just a brief primer on synthesis. If you want more work on alkynes, remember that Stromanis chapter 11 was alkynes, and Stromanis chapter 18 is actually a synthesis workshop. So if you want more practice doing synthesis and looking at retrosynthetic analysis, it walks you through this whole process and gives you many examples that you can practice on, and it does kind of guide you through the choices. Good luck.